All right, welcome to chapter 4, part 4. We are talking about Newman projections in this video. So there are a few different representations of alkanes that we're going to cover this week. And Newman projections allow us to really analyze the geometry and the positioning around looking down one specific carbon-carbon bond. So we already know wedges and dashes give us some 3D information. Sawhorse is another option. You're not going to really see me utilizing that one. But Newman projection takes us, and so right here we're looking at ethane. You have CH3, CH3, and instead of looking at it, from the side of the sigma bond or at an angle, we are looking directly down that carbon-carbon bond. The first carbon is this point in the front, and the second carbon is represented by the circle in the back. Now, since we've got one carbon and two carbons, the first carbon is attached to three hydrogens, right? So we just put them in, kind of separate them evenly. And then the back carbon also has three hydrogens. Note that what is attached to the back carbon is attached to the circle, doesn't go all the way into that inner dot. This is ideal for comparing something called conformations. You may see or hear the word conformers here. Conformers are not isomers. Conformers are two representations of one molecule, right? Just different orientations in space, right? So we're not reconnecting any atoms. Everything is still connected the same. There is an ability to move from one to the other. So we're going to learn about stereoisomers in chapter 5, and that's a little bit different. Things are locked into place. But here we have a single bond. So all of these hydrogens can spin around and rotate and change positions because they can spin, not because they detach and reattach. All right, so a lot of times you'll see this representation here of the eye telling you which bond to look down. And so if we are going from the perspective of this eyeball right here, those red hydrogens are attached to the front carbon, the blue hydrogens attached to the back carbon. And this is a Newman projection. This can be really helpful with discussing the most stable arrangements and more interesting molecules, right? For instance, here we have a 2-chlorobutane, and we are looking down the C3-C2 bond. So C3 is in front, C2 is in back, based on where that eyeball is located. We see that carbon 3, right, with bond line structure, we know there's two hydrogens. So on C3 in the front, we have a methyl group and two hydrogens. The carbon 2 is in the back. It's attached to a chlorine, a CH3, and then, of course, there is also going to be a hydrogen. And so you see your chlorine, your CH3, and your hydrogen. Now, there's something that we're going to be discussing with these Newman projections, some important vocabulary here, and this is the dihedral angle or torsional angle. Both of these are important vocab terms. Even if I don't ask you a question specifically about the vocabulary, I will use that vocabulary in test questions, so it's important you understand it. You will also sometimes see the little symbol here for dihedral angle instead of it written out. That little symbol is just saying, hey, the angle here is 60 degrees. So one thing to note is the farthest apart that one in the front can get from one in the back is 60 degrees. Now you are going to see larger angles comparing, say, let's erase this, comparing, say, this front hydrogen to this back hydrogen, but it can't get any further away than 60 degrees from something, okay? Now, something that you are going to learn over and over again is electron density prefers to spread out. So the most spaced out things can be, the most stable it can be. So there are two different conformations that are really important for you to know up front. And that is the staggered versus the eclipsed conformation. Now with ethane, it's very simple, right? The only things hanging off of that molecule are hydrogens. So in the staggered conformation, all of the hydrogens have dihedral angles of 60 degrees with hydrogens on the neighboring carbon. The eclipsed conformation, right? So let's put, dihedral angles of 60 degrees. The eclipsed conformation, the dihedral angle is 0 degrees. Now it looks like they're still offset a little bit. Well, that's because if we drew them right on top of each other, you couldn't see them. And so we offset them just ever so slightly. So you can still tell that these hydrogens are right on top of each other, but you can also still see both H's, right? So it's just slightly offset for visual purposes. This is going to be the lowest energy conformation, and this is going to be the highest energy conformation. Because, and you can build your models here. Chapter 4 and Chapter 5 are really helpful, are the chapters where modeling kits can be really helpful. So if you build that out, you will see from the side, the hydrogens are as far apart as possible in staggered. They are a little bit closer together in eclipsed. We refer to this as torsional strain, right? So it adds a little bit of energy, right? It's higher in energy, not torsional energy. What am I saying? Sorry, torsional strain. We're going to be talking a lot about different types of strain. What can make compounds more or less energetic? Strain always increases the energy. Torsional strain comes from suboptimal dihedral angles. Right, so what this tells you at any given time, right, you have a bag of ethane, right? We're carrying it around in a bag today. And it has enough kinetic energy that you are getting free rotation around that single bond. Well, when we say enough kinetic energy, we're talking about enough energy to get from staggered to eclipsed, right? It's usually a small amount of energy. You see it here in this energy diagram. This is showing what happens as the, we'll blow this up a little bit here. With the red highlighted hydrogens, we're following their relationship, right? They're 180 degrees apart in the beginning. And as we start to twist the top carbon, are we twisting the top? Yes, the top carbon, right? We get to an eclipsed conformer, and it's higher in energy. And it can keep rotating, right? So that red hydrogen is getting closer and closer to the red hydrogen in the back. And then as you keep twisting, it's getting further away again. Notice all of the staggered conformations are the same energy, right? They all have hydrogens that are 60 degrees apart from each other. All of the eclipsed are higher in energy, but they're the same energy, right? It's all hydrogens lining up on top of hydrogens. And so what will happen is, yes, there is free rotation, but at any given time, a larger percentage of your molecules will be in that staggered conformation. So when we're talking about reactions and we're looking at bonds breaking and forming, knowing the geometry of our most stable conformers can be part of that discussion. So that is one reason that we are talking about that today as we are building our building blocks, our foundation for organic chemistry. It's not necessary that you know individual energy amounts, right? Each torsional angle strain that you get, each eclipsed hydrogen has a certain amount of energy associated with it. And that adds up to give you the total cost, right? The total amount of torsional energy, right? It's the difference. This is important to note because hydrogens are all the smallest element, right, that you can get. And so as we start to look at more interesting, larger molecules than ethane, we start to get larger energy costs. And we're going to talk about that. Now, on the next slide, they're just showing you a molecular orbital. The gist here is when you have these electron clouds that overlap, there can be a stabilizing effect, but it's a little bit more complex, and we will talk more about that effect in organic 2 when we talk about conjugation and aromaticity. For now, I want you to think of it as you have these filled orbitals, and the closer they are together, the closer the electrons are together. And what happens when like charges get near each other? They want to repel. And so that's why you get that higher energy from those torsional strain angles. Now, we see the same type of diagram here for propane, right? So what we're doing here is we are looking down the C2-C3 bond of propane. So that front carbon has a methyl group and 2 hydrogens. The back carbon has 3 hydrogens. And we see the same thing. All of the staggered are low energy. All of the eclipsed are high energy. But now the energy difference is a little bit bigger. It was 12 for ethane. It's 14 for propane. That's because the CH3 is bigger than a hydrogen. So when the CH3 eclipses a hydrogen, you're getting a little bit more torsional strain, right? And so you can actually see the hydrogens covering each other or eclipsing each other has an energy increase of 4 kilojoules per mole. But the methyl group in the hydrogen has a difference of 6 kilojoules per mole. Again, the exact numbers I don't want you to focus on. I want you to focus on this trend, right? The larger the thing hanging off the carbon is, the bigger the torsional strain when it's eclipsed. Then things get even more interesting, right? Now we're going to look at butane. We're looking down the C2-C3 bond of butane. There is and I'm just going to start, I'm not going to draw all of them, but here we go. C2 in front, connected to a CH3, a hydrogen, and a hydrogen. C3 in the back, also connected to a methyl group, a hydrogen, and a hydrogen. All right, so this is a 4-carbon chain. I started with this one because I already know that is the lowest in energy. Notice this energy diagram isn't oh goodness. The difference in the energy minima and maxima are not all identical like they were in ethane and propane. And it's because you have 2 larger groups. So all of the staggered are still the lowest energy levels, but there is an energy minima and a global minima, right? So with the methyl groups as far apart as possible, you get the lowest energy possible. When they are staggered, but the CH3s are closer together, it's still a local minima, but it's not quite as low as when the CH3s are spread out. Remember, we want to spread stuff out as far as possible when it comes to charge density, right? We saw that with resonance. The more resonant structures you have, the more stable it can be. Here, it's more just like physically separating these larger groups. And then when you go to the eclipsed, you notice the same thing. There are local maxima, and then there's a global maximum. And it has to do with the size again. The CH3s eclipsing just hydrogens is definitely going to be higher in energy than any staggered position. But when the CH3s eclipse each other, that's going to be the highest energy. You're going to get the big groups as close together as you can in a conformation. That's going to be the highest energy conformation. So these are all lower energy, more stable. We expect to see those angles in a larger percentage of our molecules at any given time. This is also referred to as, let me see if they say it yet. No, not yet. We want to talk a little bit about the vocabulary here. So now we need something that tells us a little more than just staggered or eclipsed, because now we see, right? Not all staggered are created equal, not all eclipsed are created equal. So there's a little bit more vocab. The most stable when the largest groups are farthest apart is called the anti-position, right? The methyl groups are anti to one another. It is a 180 degree dihedral angle between the two highlighted groups. Gauche is also an important vocabulary word. It is still a staggered conformation, so it's still lower in energy, but it's not the best one. It is going to have that dihedral angle of 60 degrees between the two highlighted substituents there. There are two gauche positions. If we rotate that methyl group all the way around, right, there is one anti-position, two gauche positions. Now, I'm going to draw it over here because they don't necessarily talk about it in Klein, but I'll use it. When we see the methyl group eclipsing a hydrogen, and then a hydrogen eclipsing this methyl group, this is referred to as eclipsed. But to differentiate it from when the two large groups are eclipsing each other, right? This is these are all eclipsed. They're all higher in energy. This is the highest in energy. You will hear me refer to this as fully eclipsed. It's how I learned it. I don't know that it is a universal thing. Anti and gauche are very important vocab words. Eclipsed and fully eclipsed can just be helpful when discussing those higher energy conformers, those less stable conformers. Again, you can do the calculations and get the number. I'm not concerned about the number specifically, but more the trend. So you see, we went from 4 kilojoules per mole when the H's eclipse each other to 6 when H and CH3 eclipse each other to 11 when 2 CH3s eclipse each other, right? So you can start to see, right, this pattern. There is the torsional strain, that is all of the eclipsed conformers are higher energy, but there is also the steric strain that comes into account. It's the difference between the two hydrogens overlapping versus the two methyl groups overlapping, right? Steric strain has more to do with size, with just physical size. When large groups get close together, we often will refer to that as a steric strain or a steric hindrance. It's different from torsional strain, right? They both stem from the electron clouds getting too close together, but they are defined differently, right? The torsional strain is simply about the dihedral angle. The H's eclipsing each other, torsional strain. The methyl groups eclipsing each other, torsional strain. The steric strain explains the difference. Why two methyl groups overlapping would give you an 11 kilojoule difference, whereas two hydrogens overlapping give you a 4 kilojoule per mole increase in energy. All right, so torsional strain and steric strain are things that you are going to hear a lot in this next chapter or two. So when we compare the conformers that you see in this little table, right, when the hydrogens are overlapping, that's just torsional strain. When the hydrogen and the methyl group are overlapping, it's still torsional strain. When you get the two methyl groups overlapping, it's torsional and steric. But when you get the gauche conformation, it's just steric because it's staggered. You have the biggest dihedral angle you can without going to anti. And so it's really just the steric interaction that causes it to be a little higher in energy. All right, in the next video, we are going to get into cycloalkanes and chair conformations. So see you in part 5.